The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so this is 2.110 6.050J, information, entropy, and computation. I think everybody here looks like they're in the right place. Okay, so are there questions from last time? It was so stunningly clear that there are no questions at all. That's how I'm trying to interpret this silence.
You're just that good.
I'm sorry?
You're just that good.
Yeah, right. That's right. Well, yeah, I mean, optimism is good, is always a good thing. Okay. All right. So let me ask you a question then. So I should say, by the way, I should warn you that my method of teaching is the following. If I ask you, if I ask you a question, right, then I'll wait for an answer. And I lived in England for years. I'm capable of waiting for a long time through, no matter how embarrassing the silence, because conversations in England consist primarily of embarrassing silences. Right? That's how people, it's kind of a Morse code sort of thing, right? So now if nobody answers the question, then I'll answer, so are you in the right place?
No.
There you go. Too bad, you're welcome to stay. All right. So actually what I really prefer is for you to ask me questions, right? That's the first thing. I would really prefer if you ask me questions. If you don't ask me questions, then I will resort to asking you questions, and then we get the embarrassing silence thing, right? And if you don't answer the questions, then finally I'll resort to actually telling you stuff that I think you should know, which is bad for everybody because, first of all, you don't get the questions answered that you want answered. And then it's bad for me because I have to think of something to tell you, right? Okay, are there any questions about this way of doing things? Okay, so that means I get to ask you a question. Soon you'll catch on and realize it's good to have some questions ready so that I don't have to ask you questions. So yeah, anybody want to give another stab at what information is? We never resolved it last time. But we sure as heck chatted a lot about it.
I have a question.
Yeah.
What is information?
No. Should have asked that before. Given that what we talked about last time, nobody really wants to give it a shot? Yeah?
Is it sufficient to describe information as a change in entropy, or are there other requirements?
Yeah, so that's actually a pretty good answer. So one way of saying information is a change in entropy. And that actually is probably the closest you're going to get as a technical definition of information. Okay, so yeah, so remember that we have, let's just do a little bit of review. A bit of information is the distinction between two states, 0, 1, yes, no, true, false, heads, tails, etc. They have to be distinguishable from each other. Oh yeah, 0 volts, 5 volts, etc. Okay. Now, quite obviously, 2 bits is the distinction between 4 states. Like, 0, 0, 0, 1, 1, 0, 1, 1. See, this is all very boring. We've all been through it before. And if a system has n states, that means that it can register log 2 n bits. Right? So something that has 3 states can register log 2 or 3 bits, somewhere between 1 and 2 bits. I forget, what was it again? It was like 1.5783621. Somebody calculated it for me last time, bits. I'm sure that that's wrong. Right, 3 states as, number of bits is greater than 1 and less than 2. Because actually, if you think of it, we can label 3 states with the following bits. We use, we can say the first one is 0, the second one is 1, and the third one is 0, 1. So half the time, most of the time, we only use 1 bit, but then we use 2 bits to label the third one. Right? Okay. Now, this tells us what entropy. So this is amount of information. So even though information is hard to define, amount of information is easy to define. It's a heck of a lot easier to define information than it is to define, say, energy. It took people a long time to figure out how to define energy. And energy, it requires you to say, there's work, and here's a certain amount of work, and there's heat, and here's a certain amount of heat, and here's a ways of turning work into heat. And now we're going to have like a common way of measuring the amount of heat in something, like the calorie is, what is a calorie, by the way? How's it defined? Just checking.
It's something about raising like a certain amount of water 1 degree.
Yeah, you're right. Right. How much water? A cc, right, a cubic centimeter, 1 degree Celsius or 1 degree Kelvin, exactly. That's right. So, it took them a long time to figure out, these techniques for figuring out how to measure energy. But if you want to measure information, then there's a very simple way of measuring information in terms of bits. And that makes life a lot easier. In fact, that, I think, is what, if you want to know, that's what makes it possible to teach this course. Because if you look at the kind of concepts that we're going to be teaching, that you guys are going to be learning in this course, despite the fact that most of you are freshmen, many of the concepts are concepts that don't get described to most people until they're graduate students in physics or chemistry or engineering. So, and the reason that we can do this is part of it, the fact is that you're MIT students, and I know some of you are graduate students and not freshmen. I'm not trying to insult you. So that you're very well prepared and very smart. But part of it is that, in fact, the basic ideas behind information theory and, by extension, behind ideas about entropy and statistical mechanics are actually pretty darn simple. Okay, and this actually tells us what entropy is. Entropy is information. If you look at that expression, S is equal to K log W, which is inscribed on whose gravestone? Boltzmann. I should mention, by the way, that if you look at the quizzes for this course, knowing what's inscribed on whose gravestone is an important kind of thing. It's an example of something that it's good to know. Hint, 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 you know what I'm saying? To do well on the quizzes. Like, there are all these sections in the quizzes that include things like who did what. Typically, they're not too hard. You don't have to remember 100%. 90% will do. Okay. And then there are also sections on buzzwords. Buzzwords like information, entropy, stuff like that. We're going to quantum computing, quantum bits, qubits, buzzwords, things like that. Because shockingly enough, a big part of what this course is about is to teach you buzzwords and teach you how to use them. And the purpose of this is actually, remember that, sad to say, I think Paul and I can both tell you that even though we probably did very well in college, I personally, I won't speak for you, I personally have forgotten a lot of the individual things that I was told. And I've forgotten how to do certain sorts of calculations, which I really should know how to do. Lots of stuff that I should know how to do, I've forgotten. But I still remember the buzzwords. Like, I know how to use the word entropy. So it's actually very important, right? Later on in life, once you've forgotten the actual content, when you're at some cocktail party, right? You know, and you're sitting there with your drink in your hand talking to somebody else. It's very important to be able to say with complete confidence, even though you've forgotten what it actually means, you know, well, you know, a proton makes a perfectly fabulous qubit, right? Why? Because it's a spin up, a spin down, right? You know, so if you can do that later on in life, then actually this course will have accomplished much of its goal. All right?
So you know the definition of education, don't you?
No, what's education? What is it?
It's what's left over after you've forgotten everything you learned.
Right. Yeah, there's definitely something to that.
Yeah.
Education, you know, what does anybody know what the Latin roots of the word education are? Lead out, yeah. Ex ducere, lead out. It's kind of like, I like to think of it as kind of like what happens when you make a wire, right? You have this metal and you draw it out through a little orifice, squeezing it out. You can think of it in pasta if you want instead of a wire, right? Smushing it into this like tiny narrow shape and kind of pulling it. It's a painful process for the wire itself, right? It's also difficult for the person who's trying to actually pull the wire out as well. Anyway, if this course really gets to be like that, then you're certainly free to drop it. Okay, so entropy is information. Remember, this is, what's this called? Buzzword time? Boltzmann's constant, excellent. The buzzword alert is we're in good shape. So this is Boltzmann's constant. I won't write it down again. It's 1.38 times 10 to the minus 23 joules per degree Kelvin. Okay, important thing to know these. You know, actually, one thing I noticed, so it's people from different countries here I notice, and I don't want to criticize American students, I having been one myself too much, but one thing I notice about students from other countries, particularly graduate students from other countries, is that they actually know the value of Boltzmann's constant, and they know things like the charge and mass of the electron in physics, and that's incredibly useful to know, right?
Can you say that again one more time?
The insulting the American students thing? Yeah. I'll write it down. Yeah. And the reason is, if you don't know these, then you actually don't really know the kind of relevant scale of certain kinds of events and certain kinds of phenomena. So, and if you don't know the relative scale of certain phenomena, then very embarrassing things can happen to you, like what happened to a certain never-to-be-named physics graduate student at MIT. He was doing his work on quantum optics, and during his qualifying examination, one of the examiners said, "So tell me, what's the wavelength of visible light?" And this guy, you know, he was a graduate student working on quantum optics. He thought for a bit and then he said, whereupon he immediately failed. They told him to come back later when he actually knew something. Okay, so this shouldn't happen to you guys. You have lots of time left to prevent it from happening. Okay, so entropy is information. So you could say that this is the number of microscopic states or configurations Planck, who, remember, Planck actually, what was this constant originally called? Now we're getting to esoteric stuff. What was this K originally called? Planck's constant. Good. Now that's very good cocktail party fodder, right, later on in life. Right, yeah, so Planck, who originally wrote down this formula, which is inscribed on Boltzmann's grave. So Planck called these, actually, he had a nice word for them, complexions. That's the number of microscopic complexions of, say, atoms and molecules. The number of different ways that they can, the different hues and different ways that they can take. So that's an L right there. It just fell between the cracks.
What language is complexions a word?
It's a strange word. I think it's a funny word because actually it's a combination, while we're on the subject. Complex is a Latin word. The Greek version of this is simplex, S-Y-M-P-L-E-X. So complex is actually a Latin word, and it just means having several layers, right? But anything that ends in IONS or ION is a Greek word because ION is the suffix for neuter items as opposed to masculine, which are typically IOS or iota omicron and sigma, or feminine, which are typically iota alpha. Yeah, so I think he just made it up. It's not a real word. I think, so far as I know, that's where it comes from, is from Planck doing it. Don't ask me why. Later it was, later it was taken over by the cosmetics industry and used much more, but misspelled differently. Okay. All right. So you see right here that S is just equal to the amount of information. So this, by the way, this is actually the natural logarithm, because when they wrote this on Boltzmann's grave, they didn't have a separate symbol for log base 10 and natural logarithm. So they meant natural logarithm even though they wrote something that looks like it's log to the base 10. Okay? So this right here is actually equal to Boltzmann's constant times the natural logarithm of 2 times log to the base 2 of W. Oh, over, excuse me. Do I have that right? No, times log to the base 2. Log to the base 2 of W is bigger than log to the base E of W. So you've got to multiply by something that's less than 1. A natural logarithm of 2 is less than 1. What's the value of E, by the way?
2.7.
2.7. All right, good, great. That's good. You'd be amazed at how many mechanical engineering undergraduates don't know the answer to that question. Even to the 2 points, not even the 2.7 part, they don't know. Shocking, isn't it? Okay. All right. So this is just, some normalization, and this is the information in these microscopic little doohickeys. The information in the complexions of this gas, this physical system, this desk, etc. Right? All right? So I'm just reviewing this, but tell me when you get bored. And I'll go, but I think this actually fits in quite nicely, and I typically start each class with a review. That's why I asked you if you have any questions about last time, so that we can talk about things that might have been unclear. Though I'm still basking in the belief that what I said last time was so unbelievably clear that there were no questions about it. Actually, I don't believe that. But okay. So now let's get to your definition, which was a good one. All right. And it shows it actually the fact that you gave this definition that information is decrease in entropy or change in entropy, that shows that actually something happened while the wire was being pulled out last time. Okay. So information and there is, so this is a question and here is an answer. The answer is change in entropy. So the thing about entropy is, and this is a point that causes lots of confusion, and it's actually hard to talk about in a way that's not confusing. So I will probably confuse the issue further, though I will try to say things that are correct. So because we don't know what the actual configuration of the atoms and molecules in this room is, entropy is usually taken to mean information we don't know. We don't have it. We don't have this information. And it's a darn good thing that we don't have the information about the positions and velocities of every single atom in this room, because since that amount of information is at least as big as Avogadro's number of bits, 6 times 10 to the 20. Well, what's Avogadro's number? Let's get it. All right. Hey, people in this class know a lot of stuff. That's great. Okay, yeah. So the number of, and what is Avogadro's number? No. What's the numerical value of Avogadro's number? What is it? Right? It's
things in a mole.
Number of things in a mole. Yeah. What's a mole? 6.022 times 10 to the 23rd things. Okay, all right, never mind. What is a mole? Not the number.
Number of atoms in 4.01 grams of carbon.
Right, that's right. It's like basically the number of hydrogen atoms in a gram. Right. They chose to define it in terms of carbon. I don't know why, because
Carbon's awesome.
Carbon's awesome, that's right. Because they wanted to confuse people because there are different isotopes of carbon, right? So, but anyway, okay, yeah. So, so the answer depends on the well, never mind. Okay. So it's a good thing we don't have that, because in fact, Avogadro's number of bits is a very large number of bits, and it would not fit into all of our brains if we tried to cram that amount of information in our brains. They would explode, right? And in fact, you can see right away that the amount of entropy in this room is much larger than the amount of information we can remember, because our entropy is part of the entropy in this room. And the number of configurations of, the logarithm of the number of configurations of complexions of me, right, if my complexion is particularly ruddy today from running around outside, the number of different complexions, I as a thing cannot store more information than the logarithm of my number of complexions, and that includes my brain, right? So I myself personally contain, way more than Avogadro's number of bits, but most of those bits are not anything I'm particularly proud of. It's like bits that have to do with, the microscopic motion of a molecule, like the fact that this little piece of skin is flaking off, right? Okay, so entropy is typically referred to as information we don't have, okay? And this actually causes lots of trouble, as we'll see later on in the course, because what that means is that when you find something out about a system, get information, reduce entropy. Ouch. When you get information about a system, you reduce its entropy. And you reduce its entropy by exactly the amount of information you've obtained. Which is why, in fact, this is a really good answer to what is information. And in fact, it's a very clever answer, because you note that you kind of really actually changed the topic. Because last time we were talking about what is information, and people were trying to give qualitative differences in definitions of information. And you sneakily changed this into a quantitative question, saying, how much are you reducing entropy? How many bits, right? And then it becomes actually a very reasonable question, and it has got a good answer, right? So, whoops. Here is a penny. I want you to verify that it's a real penny and not one that has two heads, okay? Because I know that already, even though it's only the second lecture, I know that you don't trust me, okay? Okay. Now, how many bits of entropy are in whether the question of whether that coin is heads or tails? 1. This coin, in the fact that it's heads or tails, there's 1 bit of entropy. There's a heck of a lot more entropy in the microscopic motions of the little copper atoms in there, but let's ignore that for the moment. All right. So now I'm going to look at that. So, how much I actually know what it is. And you may notice I'm not telling you whether it's heads or tails. So what's its entropy now? The unknown information, so far as I'm concerned. 0, right. So how much did the entropy change by, so far as I'm concerned? 1 bit, right. So how much information did I get? 1 bit, exactly. But here's a problem. I reduced the entropy of this coin by 1 bit, so far as I'm concerned. But so far as you're concerned, how much entropy does it have? 1 bit, right? So what for me is a bit of information, I know what it is, for you is a bit of entropy, okay? And this is a problem because the quantity entropy in statistical mechanics and physics is not supposed to be some namby-pamby humanitarian subjective kind of thing, that depends whether the Pope says it's a certain way or not, and I'm treading across the line again. Well, of course, the Pope recently has really been treading across the line. And talk about treading across the line, my goodness. What was he thinking? Okay, yeah. So it's not supposed to be subjective, the entropy, and yet here it is, obviously subjective. By the way, it's heads, and you can verify that. What?
What if you lied to us? What's its entropy?
Oh, okay, yeah, well then that's a good question. Yeah, that's even worse, because you think that its entropy is 0 bits, but in fact you are so wrong. You want to check, I didn't move it.
Yeah, it's heads.
Okay, see, since you obviously don't trust me, which is probably very sensible of you, I got him to verify that it's heads. Okay, yeah. So, was that sufficiently confusing? I think the point is that entropy is information you don't have, okay? And what people normally call information is information you do have. Entropy is information you don't have, information is information you do have. Is that sufficiently confusing? Yeah.
When you say that it's 1 bit of entropy in our minds, is it really like, let's say there are 10 or 15 people in the room, is it really 15 bits of entropy then, or is it?
No, it's actually, no, that's a good point. It's actually just 1 bit, right? So, and we can see this now that everybody knows that it's heads, it's still heads, okay? Still heads, it's heads. Everybody knows that it's heads. That's 1 bit of information, but it's one that we share. And what that means is that we have what's called mutual information. So there are like, I think we now have more than 15 people. There are like 17 bits of mutual information that we each know that it's heads, where there's only 1 bit, but it's the same bit. We each have a different, in our mind, the memory that it's heads. That information is, a different bit, but they're correlated with each other because we all think it's heads, except for the people who think that, or really conspiracy theorists, and think that he and I are in cahoots with each other, all right?
So what happens after you flip it, then let's say you put it back in your pocket?
Yeah.
Is the entropy changed back to what it was because you don't know what it is?
What do you mean the entropy? I mean, the entropy, it doesn't actually have entropy either. It's really only a question of it's heads up or heads down, right?
Because it's not in that head state anymore, so you still, I guess, are wondering what state it's in.
Yeah, I guess, that shows that it's kind of a tricky question that we actually have to worry about whether, what we mean by heads or tails. Heads typically means that it's lying on a flat surface and the heads part is pointing up.
But
right. So once I put it in my pocket, then it's actually the question of is it heads or tails is no longer really a question that has any kind of definite answer.
The information was lost. If you repeated it again, the new result would mean nothing to the old results.
Yeah, this is why actually people use coins, flipping coins, as ways of deciding, making supposedly chancy decisions. It's also why they don't use two-headed coins to make chance decisions, right? Because then the correlation from flip to flip is rather high. Who here has ever read or seen the play by Tom Stoppard called Rosencrantz and Guildenstern Are Dead? Ever been in it? No, anyway, so how does it open up? Do you remember?
I don't remember.
Yeah, they're flipping coins. They're like playing the game where you flip a coin, and if the other person calls it right, they get the coin. So they're flipping a coin. I believe is it Guildenstern is flipping the coin, and I believe in Rosencrantz says heads, and it's heads, so he gives him the coin. It's heads. And then he takes another coin out of the bag and he flips it, and it's heads. Rosencrantz calls heads, it's still heads. He gives it to him. It keeps on going and going and going and going and going. It's always heads. From which you can conclude what?
Did an improbable event happen?
How improbable is it? It wants you up to about 100.
So improbable, it's probably never going to happen.
Exactly, right. It's very, very unlikely that in all the times that people have flipped fair coins 100 times in the entire history of human beings that they've ever come up heads 100 times in a row. In fact, it's very unlikely they've come up heads 50 times in a row, right? Because actually 2 to the 100 is what? In terms of 10, chance is 1 out of 2 to the 100, which is 1 out of 10 to the 30, right, exactly, see? Lots of education happened last time around, right? So, 10 to the 30 is a big number, right? 10 to the 30, that's the number of around, my guess, it would be about the number of atoms in this room. So, on the same order. So, people have definitely not flipped coins 10 to the 30 times in the course of human history. And if they tried, they would have failed. Yeah, so it tells you either the coins are fake, but I think what it actually is meant to tell you is that something very much not obeying the ordinary laws of information, physics, and probability is going on. In other words, it tells you that it's a play. Right. OK. All right. So when we get information, we reduce entropy. And this, as we'll see later on, this becomes a problem because entropy, the entropy that figures into the second law of thermodynamics, which governs how heat engines can operate, is supposed to be some objective quantity, and is not supposed to depend on, whether you or I or Pope Benedict knows whether a coin is heads or not. But we'll actually see that there is, in the future, we'll come up with actual situations where, in fact, if you get, or if some being, some entity, some thing, and these things actually, ironically, happen to be called demons, if a demon gets information about a coin or a spin of a proton, for instance, then by getting that information, the demon really has reduced the entropy of this proton and can use that information to extract work from it. So there actually really is a direct trade-off between information you possess and your ability to make systems do work. So it's not so namby-pamby humanities, Rosencrantz and Guildenstern are dead after all. There actually is a truly objective quality to information, and quantity of information is important. OK? OK. All right. Now, let's see. I'm tempted at this point because actually this is pretty much the end of the review of last time, but I was in the middle of rushing through telling you about the information and finance. Do you think it would be shall I tell them? Shall I tell? OK, here's your vote. We can talk about coding, which is what we're supposed to be talking about, all right? Or we can talk briefly more about information and finance for this paper of mine, which is, by the way, entitled The Black Hole of Finance, because it relates things like black holes and gravitating systems to financial systems. Who wants to go right on to coding theory? You'll still hear about coding. Who wants to hear about the black hole of finance? OK. All right. Sold. All right. And I can do this quite easily because the information is still up on the board. And I'm using information in the sense of information you possess. So let me just remind you, so this actually will be OK, because in fact, let's talk just a little very briefly right now about things we'll talk about more later on in the course. This is the problem with actually talking about interesting stuff, is that the carefully planned outline of the course gets a little jumbled up, but that's OK. It's all right. So remember, we have this thermodynamic entropy right here, and in a thermodynamic system, and I guess over here we'll do finance. So entropy is a function of energy. So if I heat up the molecules of gas in this room, then they have more entropy. And it's actually not hard to see why that's true. What's happening is, OK, they occupy the same volume, but they're moving around faster. And they could also move around slower if they want as well. So they have at least as many possible complexions or configurations as they had before, and quite a few more in addition, right? So it's not, of course, it's not always true that entropy increases as a function of energy, but it typically is. So here is S of E. Now, the quantity, the derivative of S as a function of E, this is actually 1 over the temperature. So that's what the definition of temperature. I know this doesn't necessarily look like what you think of as temperature, but actually once people like Maxwell and Boltzmann and Gibbs and Planck, of course, since he wrote down this formula, realized that there was a nice, simple, straightforward mathematical interpretation of what entropy was in terms of what we would now call information. So they didn't call it information because nobody cared about information theory back in like the 1860s. Okay, right? All right, but so once they realized this, they said, oh, well, now we know what entropy is. What's temperature? And they said, oh, look, temperature turns out to be 1 over the derivative of entropy with respect to energy. OK? And remember, this is temperature. So this is temperature. And heat flows from hot to cold. You know this. But why does it? Because that increases entropy. And the second law of thermodynamics says that entropy increases. Actually, it says that entropy, you got to be careful. The second law of thermodynamics says that A, entropy doesn't decrease, and then B, it tends to increase. Okay. So why does it do that? So entropy is, it's the logarithm of the number of ways that energy can rattle around in a system. And if there's a way for the energy to find a larger set of ways to rattle around in the system, it will do so. Just because there are more ways to rattle around in the system. Okay? It's actually pretty, in some sense, at an intuitive level, it's pretty simple. Okay? Now, so why does heat flow from hot to cold? It's because that same amount of energy, if it's in a hot thing, and it flows to a cold thing, it can increase entropy, right? That's what temperature says. High temperature means low dsDE. I add a certain amount of energy. At high temperature, it means I increase the entropy by only a little. Low temperature means high dsDE. I add a certain amount of energy. At low temperature, I increase S by a lot. So if I've got a bit of energy in a hot system, from molecules rattling around, and that energy can find a way to go to a cold system, then it's got many, many, many different more ways to rattle around. And so it will tend to do that, by and large. Right? People happy about this? And we have the quantity specific heat, which corresponds to dt dE. It tells you if I take, if I have this hot system and energy flows from the hot system into the cold system, how much does the hot system cool down, and by how much does the cold system heat up? So this is what this quantity tells you. Right? The specific heat tells you, oh, I pop in a joule, how many degrees, I pop a joule into the system, by how many joules does it heat up? And if you just put that in there, we get minus T squared E squared S dE squared. The fact that I wrote this all down last time actually makes life easier, even though it makes it more dull. And the important thing is that this actually can be negative. Because right here, and this is where we ended up last time, this has positive C because d squared S dE squared is negative. A curve like this, however, for entropy, this has negative specific heat because d squared S dE squared is positive. So we're not accustomed to things that have negative specific heat. But lots of them actually exist and are out there. All right? I don't think that there's anything, there's not, actually there are some I was going to say there's nothing in this room that has negative specific heat, but you really got to be careful about saying things like that, so maybe I'll be careful. There are certain very microscopic systems that are dominated by surface effects that seem to have negative specific heat. But the one example of systems that I do know that have negative specific heat that are very common are systems outside of this room. In fact, a big system that we're part of. So, example of specific heat less than 0 are gravitational systems. So if I have a cluster of stars or planets, or even a cluster of dust, like a huge cloud of dust out there in interstellar space, that's bound together by the force of gravity. So it's or a star cluster. So the star cluster is bound together by the force of gravity and all the stars in the cluster. There's a famous theorem called the virial theorem. How many people here have encountered the virial theorem before? Yeah, if you take a course on classical mechanics, like not the kind that you took in high school probably by and large, but a fancier course on classical mechanics, then they'll probably tell you about this. It says that if you have a bound system, like this a system in gravitation, it's held together by an attractive 1/r² force. then it's actually quite easy to prove, and this was proved back, I think, in the 1600s, that the average kinetic energy of the system, which I'll just call it K, is equal to minus the average potential energy. The potential energy is negative, right? Because the potential energy in gravitational system, it goes as minus G m m m1 m2 over r. That's how the potential energy goes. And the kinetic energy, of course, is positive. And actually, you know that the potential, because the system is bound together, you know that the magnitude of the potential energy is bigger than the magnitude of the kinetic energy, because if the magnitude of the average kinetic energy were bigger than the potential energy, the system would go, everything would go flying off all over the place, and it wouldn't be bound together. So you know that the magnitude of K is less than the magnitude of U, and it actually turns out, on average, to be 1/2. And this 1/2 comes from the fact that it's 1 over r squared force. If it were 1 over r cubed force, I think this would be 1/3. Or no, yeah, something like that. I forget the actual numbers. Okay? So everybody happy with this? I don't expect you, I'm going to ask you to believe me, trust me on this one, even if you don't trust me about heads and tails. Okay. Now the overall energy is equal to the kinetic energy plus the potential energy. And that's, of course, just equal, in this case, to minus K, right? Because K is minus U bar over 2. The overall energy is also minus U bar over 2, right? Because it's U minus U bar over 2. U minus U over 2 is minus U over 2. That's just minus K. Everybody see this? I just kind of breezed through that little bit of mathematical identity here. And so now you actually see, that if the kinetic energy of the whole thing is basically, n times the temperature, if I've got n particles here. The kinetic energy is basically the temperature. The temperature is essentially kinetic energy. Temperature of a particle of a gas molecule is like its kinetic energy. Times 2/3, right? Something like that, with some factor out in front, depending on the dimensionality of the system. And you see right now, so E is minus nt, or T is essentially minus E over N. And that tells you right away that DE is essentially minus 1 over N, and that's less than 0. That's negative. Is everybody okay with this? I'm encountering some blank looks. I've spent, even though I have no formal training in mechanical engineering or engineering in general, I never took a course in engineering in my life. After more than a decade of being a professor of engineering, which makes you wonder about the educational system somewhat, but after more than a decade, I actually have learned a bunch about things like feedback. And in fact, feedback for me is very important, not just at the quantum mechanical level, but at this macroscopic level. So if you understand this, just like kind of nod your head like that a little bit, give me some feedback. If you find this sort of strange, then look at me blankly, or like, shake your, if you find it wrong, just, you can go like that, right? Okay, so is everybody okay so far? Yeah?
What does the N stand for?
I'm sorry?
What does the N stand for?
Oh, yeah. Yeah, N equals the number of, stars, dust particles, or whatever the self-gravitating things are. So this has a feature. So what it says is these self-gravitating feature have the feature, if you take energy out, they get hotter. In fact, or you take energy out, the average kinetic energy gets bigger. This actually is very familiar if you look at the solar system, right? Mercury moves around the sun a lot faster with a much higher velocity than the Earth. Why? Because its kinetic energy, its overall energy is smaller. It's more negative. It's deeper in that potential well. So on average, it's got to move faster. In fact, from this, you could tell, if you knew the radius of how far of Mercury's orbit, you'd be able to tell just how much faster it goes. Similarly, Jupiter is going more slowly than the Earth.
Why?
Right.
I don't see how you can go from this to talking about orbits.
So this is true. This is true of any self-gravitating system, right? Any system held together by gravity is that the kinetic energy is equal to minus the potential energy over 2. So in particular, it happens to be true of the sun and a planet that's orbiting around it. So if you take energy out, what that says is if you make the potential energy more negative, which means you move the thing closer to the sun, then on average it's going to move faster. If you divide the potential energy by 2, sorry, you make it twice as negative, the thing will move twice as fast. You got it? Yeah. So if you take a star cluster and you take energy out by, say, removing some stars, or if it starts, radiating out, over time, the stars in the cluster will move faster and faster and faster. In fact, if you look at computer simulations of star clusters, I had a friend in high school who liked to do, this was back in the days when you had to use paper tape to program your PDP-11. Paul will tell you, I can't compete, right? But so he made this great program that followed like 100 stars in a star cluster around and saw what they did. And what they do is actually, as they're like spinning around like this, and then every now and then, just by accident, a star will go through a trajectory where it picks up a whole bunch of kinetic energy, and it picks up enough kinetic energy so that it escapes to infinity. It gets escape velocity. And when that happens, of course, the cluster has lost energy, and the other stars huddle together more closely, but they zip around faster. So if you look at these gravitational systems, the more tightly they're bound, then the faster everything's moving. And this, of course, tells you, this is very important for the universe as a whole, because it tells you why the sun shines, right? Because it says, as a ball of gas undergoes gravitational, it sends out energy, just by radiation, it gets cooler and cooler. Sorry, excuse me, it sends out energy. It doesn't get cooler and cooler, it gets hotter and hotter. And eventually it gets hot enough and dense enough that you can start nuclear fusion reactions and fuse hydrogen to helium. And when that happens, the sun starts to shine. So it's actually quite important, this whole negative specific heat kind of stuff. Of course, the other feature is that if taken too far, it can be bad, right? It's good that the sun shines, but of course what happens is if you keep on losing energy, everything goes faster and faster and faster and faster and faster. You're huddled more and more and more and more. You get denser and denser and denser and denser. Now the denser you are, the harder it is to escape, okay? It's like if I take a ball, right, of mass m, and I ask, what's the escape velocity? So escape velocity comes in the following form. Here is this ball. It's got radius r. It has mass m. And I have a little mass m, and it's going to have velocity v. So it wants to escape to infinity. Okay? Well, for it to escape to infinity, basically its k has got to be greater than minus its u at the surface, right? It's got to have enough kinetic energy so that it still has some energy once it's gotten to infinity. Which is to say that 1/2 mv squared is greater than g times big M times little m over r. Right? Everybody okay with this? Do the head noddy thing or like a head shaky thing if you don't. Is everybody okay? Okay, good. So this tells you, notice that it doesn't matter what your mass is, okay? And this actually tells you that something quite bad can happen when an object gets too dense. So suppose there's a maximum velocity, that v is less than v max, which just for the sake of argument we'll call c. All right? And the argument that I'm giving you right now, by the way, does anybody know when this is, when people, okay, never mind, I'll tell you. I want you to guess when this argument was made, how long ago. Okay? And what that says, if r, the radius, is less than 2 gm over c squared, then nothing can escape. If c is the actual velocity of light, right, then not even light. And this is a situation that's famously called what? A black hole, right. So this is a black hole. And this RS is called the Schwarzschild radius. for Karl Schwarzschild, who died in the First World War. Yes?
Doesn't that 1/2 mv squared inherent thing for energy not work when v is relativistic?
Yes, so this argument is clearly bogus, right? Because first of all, photons don't have mass, so far as we know, right? And then if they do, they certainly wouldn't have energy 1/2 mv squared. It would be more like, mc squared, right? So there's definitely some wrong factors of 2 kicking around this problem. So has anybody guessed when this argument was made? It's actually the fact that it's a purely classical argument should give you a hint. No, that would be good. That would be good. That's good. I like that. I like that spirit. Like, go further, right? Right. No, so people had to know about Newton's laws of gravitation, right? So they needed to know this. They needed to know that kinetic energy was 1/2 mv squared. People didn't figure that out until Newton was the first person to figure that out. So it couldn't have really been before like the late 1600s. But in fact, it was actually, just to give you the answer, this argument was made by the famous Pierre-Simon Marquis de Laplace in, I think, 1797, something like that. So it's an old argument. But people didn't start calling them black holes until the 1960s. OK. Yeah, so that's bad. This is bad, right? It forms a black hole. And now we know even more about black holes. The situation, oh yeah, and why does this work? And this is the right answer, right? So let's say R, if R is less than what's called the Schwarzschild radius, which is this. This is the Schwarzschild radius of the hole. And I think what's going on here is that this factor, as you rightly pointed out, this factor of 1/2 is bogus. It's definitely wrong. But when Einstein first started doing calculations in general relativity rather than Newtonian dynamics, there are several factors of 2 that show up. In fact, there's at least 2 factors of 2 that show up. And this is one of them. And there's another one that shows up. And in this case, they happen to cancel each other out. And so you actually get the right answer. You could have just as easily been off by a factor of 4 or something like that. OK. So yeah, so black holes actually have negative specific heat because actually black holes, they have the feature that so now things start to get wacky because actually for a long time people thought black holes were perfectly black. But then around in the 1970s, Stephen Hawking at Cambridge figured out that if you take funky quantum mechanical effects into account, then they're not actually black, but they in fact radiate. They have a temperature. So actually black holes have a temperature. They have a temperature which the temperature goes as essentially, KT is equal to H bar, I just want to get the units right, H bar over MC squared, and then, I'm not going to get the units right. Anyway, they go as 1 over the mass. It's proportional, temperature is proportional to 1 over the mass. The bigger the hole, the cooler it is, okay? And then the entropy goes as the mass squared, okay? Which you can see easily because 1 over T is ds dm, or dmc squared if you like. So that goes as 1 over m. The specific heat, C, is dt dE. And this is equal to minus 1 over m squared, right? Because T goes as 1 over m. E goes as mc squared. So I should write that out. Because it's always fun to, you should always, one of my rules in life is you should always, whenever you get an occasion to write down the formula E equals mc squared in a situation where it's correct, you should always do that. Right. Just, you try it sometime. You'll find it's very pleasurable. Maybe I shouldn't have confessed that on camera. Okay. So the specific heat is negative. And you can see that right away, right? Because basically the hole loses energy, and when it loses energy, it gets smaller. Its mass goes down, but that means its temperature goes up. So in fact, when a black hole evaporates, it starts out very, very, very slowly, but as it gets smaller and smaller, it goes kerblooey. And in the last microsecond of its life, it tosses out a gigantic quantity of radiation, which is yet another reason not to get too close to a black hole. And makes you kind of wonder about these dudes who want to make a black hole inside the Large Hadron Collider in CERN. Actually, it makes you feel a little better because, right, I mean, you have to be somewhat careful about building black holes because they have this other horrible tendency to suck in everything that comes around them, right? And but they're also quite dangerous because actually in the latter stage of their life, they're also highly radioactive. So they're things to be careful about. Now, don't do this at home. Okay. Right. Okay. We're still going to have time to talk about coding theory. And how many people actually did the reading? All right. Did you read the thing about codes? Okay, yeah. I highly recommend the chapter on codes. It's this one, Paul wrote all this stuff, right? But I really, this is one chapter I particularly enjoy for some reason. I don't know why. It's almost as good as writing down E equals mc squared. Okay. So, anyway, these, gravitational systems, they're unstable. They have negative specific heat. They can't be in thermal equilibrium with each other, right? Because if you're in thermal equilibrium, if you have the same temperature, two things have negative specific heat, then a little bit of energy flows from here. This one gets hotter, this one gets colder. More energy flows from there, hotter and colder. More energy flows from there. It actually, if you think it will actually accelerate, the flow of energy will accelerate. And it's chaotic because, in fact, it's sensitive to initial conditions. Because if by accident that little tiny bit of energy flowed from here to there, then this one would get hotter and this one would get colder. And then energy would flow from there to there. And it takes off in that direction. And that's why gravitation as a whole is highly unstable, and it leads to this rather unfortunate, or depending on your perspective, well, I don't know, unfortunate from most perspectives, feature of gravitational collapse and the formation of black holes. It's not a good thing in many respects. It's good because it makes the stars shine, right? This negative specific heat, as I argued before, is very important because if we didn't have it, then we wouldn't have these nice shiny stars out there, and it wouldn't be heating up. Not that it's doing a very good job today, but believe me, it would be a lot worse if it stopped shining. Okay. All right. So now let's look at financial thermodynamics. Are there questions about this? As my graduate students will tell you, you shouldn't get me talking about gravity and quantum mechanics and stuff like that because I can just go blather on forever. It's a fascinating topic, and we'll learn more about it later on. Even if I find it a fascinating topic. You may not, but we'll find out. Okay. Yeah, so as I mentioned last time around, I've been doing all this stuff about things like black hole formation and quantum mechanics and black holes and what's statistical mechanics and black holes and things like that. And I'm constantly forced to referee papers on the subject for my sins, right? So I was focusing on that. And then when the whole financial system seemed to go kerblooey and implode this last fall, which is an ongoing process actually. Nobody knows how far it's going to go. Could get bad, right? I have to say that I was intrigued because some of this weird dynamics and some of the strange, bizarre things that were happening seemed a lot like, what happens when like one galaxy cannibalizes another and like sucks off all of its stars, and then the other galaxy in a frantic effort to stop, it gets faster and faster and faster. So here you had these gigantic Wall Street investment banks, and they everything seemed to be okay. And I think, as Paul pointed out last time, you can be in a black hole and not know it for a long time, right? If the black hole is big enough, everything can look pretty normal. You have a black hole, and in fact, by some accounts, the universe as a whole we might be in a black hole, right? This expanding universe we're in could contract again and go smush. If so, that means we're basically in a black hole. Anyway, when these, of course, certain things can go wrong, right? Like you may notice, like when you're trying to shine your flashlight out there, that the light comes back towards you, right? That could be a problem. That could be a sign that you're not in very good shape. Okay. Anyway, when these banks started to realize that something was wrong, right? Something was wrong. Their negative debt, like their negative gravitational energy, was overwhelming their their money, which you can think of cash as kind of like kinetic energy, and their like assets. And you can think of this kind of like how shall I say it? So the overall energy of a system is like mc squared. That's its mass, and then you have your kinetic energy plus your potential energy. And if you think of the overall wealth of something, you have your overall assets, including intangible assets, and then you have cash, and then you have minus your debt, right? So in this analogy, this negative potential energy is like debt, kinetic energy is like cash, it's stuff you can do stuff with, and this mc squared is kind of like your intangible assets, your earning power for the future. Anyway, if you look at a black hole, you'll see that what happens is that a black hole forms pretty much right around when this negative gravitational energy overwhelms the positive mass energy and the kinetic energy, right? Because it actually forms when U is essentially minus mc squared. So when you get into debt, it's like when you've gotten too much into debt, that's when a black hole forms. And here, if your debt overwhelms your cash and your assets, then you're bankrupt, right? That's what it means to be bankrupt. Anyway, these banks, when they started realizing, gee, something is funny here. People aren't giving us any loans any longer. But not being able to get any loans is kind of like when you shine your flashlight up there and the light goes like that, right? So the signs were looking bad. And then, of course, they went into this they started like blowing off employees and assets in a frantic effort to keep them from undergoing financial collapse, and lots of people got fired, and lots of assets got set off there. But it turned out it wasn't enough, and kind of the core business, there's this gigantic sucking sound, and then at that point the government decided to step in, spending your and my money, many large amounts of it. You'll be the people who have to pay it back for longer than I have, because I don't intend to be around paying it back. Well, certainly will be paying it back for longer than I intend to be alive. Okay, so anyway, that's what happened, and it seemed to me a lot like this was a lot like gravitational collapse. It looked a lot like it. So I claim to you that it is basically. So let me show you why that is. I claim that these institutions have negative specific heat. Basically, that an ordinary bank like the MIT Credit Union, let's say the credit union, that has what we'll call positive specific heat. Your interactions with that, they can be completely stable. You can deposit your salary there, you can take it out, they'll give it to you, right? On the other hand, if you have a bunch of investment banks and hedge funds interacting with each other, then I'll argue to you that this cannot be stable. And what we kind of witnessed was something like that. So let me tell you why that is. So here's the you see right here that basically the analogy we're going to have is that the conserved quantity, energy, is going to be like money. Now money is not conserved, okay? So it's not exactly like energy, but it is conserved when you exchange it. Like if I give you $1, then you have $1 more and I have $1 less. Yeah, you would already know that I'm a cheapskate. I wouldn't give $5 last time around, right? You do really think I can give you $1 now? You can have the penny. His price is low too. Oh, now I can't find it. Oh, well. Okay. And interestingly, in gravitational systems, energy is not absolutely conserved either. Like if the universe, our universe apparently sprung into being out of nothingness with a lot of energy in it already, about 13.8 billion years ago, energy was not conserved when that happened. If it smushes down together in like a big crunch and just goes away completely, energy won't be conserved then either. So actually in gravitational systems, energy is not absolutely conserved. But it's locally conserved. Like if I send you, I send you a piece of energy. I don't know, now I should really try to find this. I can't believe I've lost my penny. Okay. Okay, it's locally conserved. And we can define entropy in just the same way as before. So entropy, as a function of your wealth, is just equal to, we'll just say, the natural logarithm of the total number of ways that you can invest that wealth. The number of options that you have. Like I can take my money, I can put some into stocks, I can put some into bonds, I can put some into the savings in the credit union, I can stuff a bunch into my mattress, which might not be a bad idea around now, okay? So anyway, it's the nice thing about this is this, I'm defining entropy in just the same way I did before, and it's well defined, right? There really are, there's just a large but finite number of things I can do with my money. Even if you have a limited amount of money, there's still a fair amount you can spend it on, right? But it's finite, okay? And so we just say, okay, let's take its logarithm. This is basically the number of bits of information, if I multiply by log2. It's the number of bits of information required to describe my portfolio, where my money is, how much of my money is in the credit union, how much is in my pocket, right? How much is in what used to be called Merrill Lynch, right? So this is a perfectly reasonable quantity to define, this financial entropy. And not only that, I claim, so S tends to increase. I claim that this actually obeys something like the second law of thermodynamics. We have to be careful because, of course, since money isn't conserved, if everything goes away, if all the money goes away, which is possible for the economy as a whole, then the whole thing can decrease. But in local transactions, it tends to increase. Now, why is that? So you have a certain amount of money, I have a certain amount of money. Suppose, and you have a certain entropy on your own, I have a certain amount of entropy on my own, stuff we can do. If we decide to collaborate and we start talking about joint financial ventures we can go into, we have more opportunities than we had before. Our total S taken together when we interact is bigger. Because we certainly have at least as many as we had before we were interacting, right? And now we have some more on top of it. So when you actually put, when you put two people into contact and get them to talk with each other and see if they could come up with, an exchange of money, if it's worth their while to do that, the answer is, well, they will have more opportunities. It's just exactly the same way if you take two bodies at different temperatures, you pop them into contact with each other, their entropy goes up. Yeah?
Isn't that, I'm a little bit confused by, if you go into a business together, you're relying on some third party giving you money, and so isn't the entropy of, their financial entropy decreasing?
Oh yeah, now you have a three-body problem. Let's just make it a two-body problem. Let's say you go to a possible investor, right?
But the two-body entropy doesn't actually increase unless you are able to gain money some other way.
Right. So let's see where does money flow. So let's say you have an idea for a business. You have a startup, and you go to a venture capitalist. All right. So what happens? So you get together with the venture capitalists. There's a certain number of things you can do. You don't have many money right now, so you don't have enough money, so you can't put this idea into play, right? The venture capitalist's job is to talk to people who have ideas to see what opportunities there are out there, right? So the venture capitalist also can't do as much with her money as she would like because she doesn't have companies. If she doesn't have companies to invest in, there's no reason for her to be a venture capitalist, right? She can't make any money. So why do you and she get together? It's because by her talking with you, there are more opportunities for her to do stuff with her money, right? And by you talking with her, if she will give you money, there are more opportunities with stuff you can do. You can actually, start your startup, right? So if you convince her that there are indeed good opportunities, she will give you the money. And that means that actually your financial temperature is lower than hers, right? Because we have temperature, we can define it in the same way. And this is just, it's just a formal definition. We'll just define it as 1 over t is ds d bucks, right? So when you get together, why does she give you the money to start your startup? It's because you can do more with that money than she can. That's the whole point of being a venture capitalist, right? There are more opportunities for you with that, the money, your temperature is lower, right? Your financial entropy, your set of opportunities goes up much more rapidly from getting this money than hers goes down by giving you the money. At a more prosaic level, why do I deposit my paycheck in the MIT credit union? It's because, frankly, I don't really, need it. And when I give them that money, they have a lot more things that they can do with it. They loan it out to other folks. And as a result, they get money back and they give me money, right? So the reason they pay interest is because they have a lower temperature than me. Right? The number of opportunities, the overall number of financial opportunities increases when I give them the money. That's because their temperature is lower than mine. Of course, the funny thing about that is that, of course, I actually, once I deposit the paycheck, I then take out, you know, $100. Why do I take out $100? It's because if I'm broke, if I have nothing, then actually I'm really cold, right? I'm financially frozen. I'm at effectively zero temperature. There's nothing I can do. My entropy is zero. I can't even buy lunch, right? And that's because actually, so I take the money out because actually I want to get it right, sort of the right level. I want to have, you know, the right number of opportunities in the course of the day.
If your temperature is zero.
That's bad, yeah.
But then.
Yeah, it means you're broke.
Doesn't that mean entropy is really high by that?
No, it means that the change in entropy is high, right? So, and you know this as well, right? If you're broke, right, if like I don't have any money at all, I can't do anything. My financial opportunities are basically zero. And then you give me $10, you know, I can do a lot more, right? Right? So this is, you know, basically what happens. I'm a kind of high specific heat individual compared with a credit union. I give them some money, it changes their temperature by only a little. But I'm rapidly cooling myself down by giving them my salary, and I've got to heat myself up by, like, you know, going to the ATM machine and taking some out. All right? Okay. So, and there's also specific heat. That's what we're talking about. So specific heat, we have the C, which is just equal to minus T squared d squared S d buck squared, which we had before. And my specific heat as an individual is positive and high, right? I don't like, I just can't absorb that much money without getting too hot and wanting to go deposit in the bank. I mean, some people are not like that, right? My wife is much better at spending money than I am, for instance. But I shouldn't say that.
Not on camera anyway.
Let me try again from over here. Okay. So, and all this business about, you know, where money flows around, this is a perfectly reasonable way to talk about it. I'm not claiming it's the only way to talk about it, but I think it's a good way to talk about it. You know, it actually says, it's just saying, oh, what do people like? Why does, you know, money go one place to another? Just like energy, it tends to rattle around in the places where there are more opportunities for it to rattle around. And the same is true of money. Okay? And you should be skeptical of this because I've only been doing this for the last couple of weeks now, or last few months now. And these are new sets of arguments. And I'm not claiming that this is, you know, 100% true all the time, the way the second law of thermodynamics is, even though, as we argued before, the second law of thermodynamics isn't 100% true all the time. But I think it's a reasonable way of looking at things. In particular, it means because things can have negative specific heat, you can have something where if you give it money, the number of opportunities starts to increase so dramatically, right? Because if we have S as a function of money, so this is positive, C greater than 0. If you have something like this, C less than 0, then you give it money, you give it energy, and it gets cooler, and you're more likely to give it more energy, more money, right? So the number of opportunities that it has is growing really, really rapidly as a function of the amount of money that you give it. Now actually, that actually sounds kind of good, right? Those sounds, if everything's going on the up and up, right, and the number of opportunities that these people have to make money is growing really fast, then they're like a hedge fund, right? It's like hedge funds say, give us your money, we can think of things that you could never, ever, ever think of for doing with your money, and because we're so smart and can think of so many different things, we'll be able to make you a huge amount of money in return. And maybe they're right. Maybe there are a huge number of things that they can do, and this amount increases very rapidly. And so that's actually quite great while, you know, everything is going well. The hedge fund is getting cooler and cooler, more and more money is flowing into it, they're making more and more money, they're giving it back to you, everything is great. The problem is, of course, that the reverse can also happen, right? Because if they start to lose money, so these guys, if they start to gain money, people say, oh, that's a great hedge fund, I can invest more money in it. But if they start to lose money, now they're getting hotter and hotter and hotter. They're losing money at a faster and faster and faster rate. People are saying, I'm getting my money out of there. And so just in the same way that their financial growth accelerates when they're on the up and up, it also accelerates their financial decrease. You know, their losses accelerate when they're on the down and down.
Wait, that means they're getting colder, right?
No, the point is, cold means you like to absorb money, hot means you like to give it out. So because they have negative specific heat, as they start losing money, they get hotter and hotter. They're like a black hole, right? The more energy it loses, the hotter it gets. So black hole, when it's growing, there's nothing like a black hole for sucking in extra energy, right? Nothing in the world. It's anything like a black hole for like taking in extra energy and getting colder and colder. But also, there's also nothing in the world like a black hole when it comes to going kerbam at the end of its life. Yeah?
The analogy also holds up fairly well because people are more inclined to give their money to a hedge fund with larger capital.
Absolutely, and why is that? So let me actually be specific about this and tell you. You don't mind me not talking about coding for the moment, right? I had to tell somebody about this. That's what I've just been doing for the last few months. Okay, yeah. So let's look at it. Yeah, everything fits together really nicely for this, I have to say. I'll tell you. So let me tell you a little more about it. So you can construct a very simple set of models, right? So this is based on what's called the famous Ehrenfest-Earn model. So the Ehrenfest-Earn model says I have n balls, okay, and I have m urns. An urn is like a big clay pot, right? He did this because the ancient Greeks used to vote by putting balls into urns. That's why, presumably, what his motivation was for talking about this. And you start distributing the balls amongst the urns. And you ask how many ways of their, actually I'll say that they're m+1 urns for the heck of it. For a moment, you'll see in a moment. And so there's a certain number of ways of distributing the balls amongst the urns. And that number of ways happens to be equal to n plus m choose m. It's basically you have n plus m, you're going to have n plus m places, you're going to pop together m, you're going to pick m of them and say these are the boundary lines between these urns. And the question is how many different ways they're putting down these m dividers in these n plus m slots. I don't expect that maybe to be that comprehensible, but if you think about it for a bit. If it's not obvious, then don't worry, this is indeed the answer, okay? And then you have S, just log W. As before, all right? And this is a very simple model, and you can ask, okay, let's look at things like, let's say, urns are slots where you can put quanta, and like the little places where you can put a particle, and n are bits of energy. So we can define things like 1 over t is equal to ds dn, etc. And you find that actually this is a very good model. For instance, if I say that the urns are little slots where I can put particles and are the particles, and I do this calculation, I find that this actually gives the entropy for the ideal gas. I get all the ideal gas laws from this. This entropy turns out to be what's called the Sackur-Tetrode equation. And this actually tells you what the entropy of the gas in this room is, where n is just particles of gas, and m are these little quantum slots. Of course, you can tell that the tricky part is how do you define a little quantum urn, right? What does a little quantum urn look like? I'm not going to tell you about that for the moment. All right? Okay. So in this normal model, what you find, if the energy is just, say, proportional to the number of particles, you find that S looks like this as a function of n. And everything is fine. It's got positive temperature, negative specific heat. It behaves just like an ideal gas. You can actually do exactly the same model for where n is the number of these stars in a star cluster, and m is the number of quantum slots they can sit in, and then you actually find that it looks like that for a self-gravitating system. So you can apply this Earn model to these star clusters as well, and it nicely reproduces the negative specific heat of star clusters. Okay, but now let's apply it to finance, all right? So, and let's do it this way. So once again, bucks is your total wealth, right? Just as we had before, it's your net wealth minus your total assets minus your debt. And now let's suppose that the amount that you get to invest is a function of how the amount of money people will give you to invest is a function of how much money you have. You would say, well, why isn't it the same? Why isn't it the same as my net wealth? The answer is that people get leverage. Do you know what leverage is? Somebody tell me, can anyone want to say what leverage is? Okay, so what's leverage? Yeah.
It's when you're given, like, if you want to invest $10, a bank or something gives you $100 so you can invest even more.
Yeah, you have a certain amount of assets and you borrow money, right, to invest it. And then if you make a profit, then you get a whole bunch more money back than you did if you hadn't borrowed the money. Of course, you better be right, because if you make a loss, then you're going to lose more money too. So you have to be kind of careful. All right? And actually, banks do this all the time. Like the credit union, an ordinary bank, if you deposit money then, they just go and loan the money out again. But there's the Federal Reserve requirement, which says they have to keep like a certain percentage, say 10% of the money in the bank overnight, every night. And then if you think of it for a moment, that's basically equivalent to the government allowing banks to operate at a leverage ratio of 10. Because for every dollar that gets deposited, they can lend out 90 cents. Out of that 90 cents, I think it's your next door at the moment, that you lend out that 90 cents, you have to keep 9 cents of that. And you find out that every dollar that gets deposited, you can lend out $10. So banks have like a leverage of 10 to 1. And some of these hedge funds and like Goldman Sachs and Lehman Brothers had leverage before they went kerblooey. They had leverage ratios of 30 to 1.
Have you heard of long-term capital?
Oh yeah, absolutely. Founded by I think that it wasn't Myron Scholes, wasn't he an MIT guy? The guy. Yeah, absolutely. Yeah, so a lot of these places are at high leverage. So then this is basically your leverage as a function of your wealth. Okay? And M is the number of investment opportunities you have as a function of your wealth. Because if you're wealthier, you have more investment opportunities. There are some things you just can't buy, like some hedge funds that won't allow you to do anything unless you give them $10 million. Some savvy investors like Bernie Madoff, who would only let you invest with him if you had like investing $20 million. And look, he got great returns year after year. Yeah.
The hedge funds who abide by regulations aren't even allowed to take the money of people who don't have net wealth above.
They're in the next room. Yeah. Who have net wealth.
Who don't have net wealth above a certain amount.
There you go. Yeah. Well, as we'll see, these features are what causes the problems. Because what you can prove from this earn model, so now you have this N and M, they're functions of dollars, right? You can show that, suppose that this goes as the amount of money that you have raised to some power alpha. And suppose that this goes as the amount of money you have raised to the power beta. Well, this certainly is going to go at least as fast as 1, right? Because you have a certain amount of money, you could just invest it, even without leverage, right? So, but if leverage increases as a function of your size, which is historically what's happened, Goldman Sachs got a much better leverage than you or I would, let me tell you. Ain't nobody out there who's going to lend me $30 for every dollar that I have in order to invest it in something. And they'd be right, too. They'd be fools to lend me that. Of course, it turns out they were also fools to lend Goldman Sachs that too, but that's another story, okay? So, so what you can show is that if alpha and beta, so if alpha is greater than or equal to 1 and beta is greater than 1, or if alpha is greater than 1 and beta is greater than or equal to 1. So if both of these grow at least linearly, and one of them grows more than linearly, then this implies that the specific heat is less than 0. You have negative specific heat. And actually, you can see exactly why that's true, right? It's just what we were talking about before. Like, if you have a lot of leverage, and it's not leverage itself that is bad. It's if you have more leverage, the richer you are. Because the converse of that, I mean, that looks great if you're making money. I think that you're in the next room over there. Yeah. That looks great if you're making money, right? You get richer and richer. People give you more leverage. Oh, great, I've got more leverage. I'll invest it more. You get richer and richer, more financial opportunities. Everything is looking really rosy, right? So you can make more money if you're operating under those circumstances. The problem arises when it goes the other direction, right? Because you have all these positions and all of a sudden you start losing some money. And then you're losing money, and now you've got to pay back the people who lent you $30 for every dollar you actually possessed, and you may not have it. So you start to unravel your positions, and actually now everything starts accelerating in the opposite direction. So these things are great. You know, having negative specific heat is great when you're making money. Why? Because as you're getting colder and colder, you're getting better and better at sucking people's money in, right? And they don't mind because they're paying them back. But it works exactly the opposite direction as well. Once you start losing money, you lose it at an accelerating rate. And in fact, if you have, just in the same way that if the only force in nature were just gravity, and there weren't things like ordinary matter. I think you're in the next room over. Yeah, that's okay. If there weren't ordinary matter to, like in the sun, right, to exert radiation pressure to hold the sun out, to keep it stable, despite the fact that gravity would like to turn it into a black hole, and would if it weren't that ordinary matter there. So if it weren't for ordinary interactions, which tend to have positive specific heat, which tend to move away the negative, you know, they compete with the negative specific heat of gravity, and you get kind of good situations then, right? Like the sun is good, I'd say. I don't want to make a value judgment, but that would be what I would say. So then you can have stability. But if everybody has negative specific heat, then the whole system is completely unstable. And just remember, just in interactions between different individuals, you think that it's stable, they're at the same temperature, but no, it's accelerating instability that's sensitive to initial conditions, and you just get these gigantic flows of heat, ever-growing flows of heat in a chaotic fashion. That's what happens in gravity on its own. And by gum, that's what happened when you know, all of a sudden everybody had negative specific heat. Because of course, many of the things that happened, if you look what happened, if you take the credit union, the credit union, okay, if it goes by the Federal Reserve requirement, then alpha is equal to 1, right? The amount of money it has is simply proportional to its deposits. However, beta is probably going to be less than 1 because the kinds of things that the credit union can invest in are actually rather limited. The credit union is not allowed to invest all its money in a hedge fund, thank God, right? Can't do that stuff. And actually, there was a big change around when was it, 1992? A big change happened with banks. Does anybody know what this was? I've been learning. I didn't know any of this stuff before. So there's this bill called the Glass-Steagall Act, which was passed during the Depression to prevent commercial banks from investing in anything they wanted to, because they figured that was one of the things that caused the stock market crash. And then in 1992, this got repealed. So commercial banks that you deposit, that you're subject to federal deposit insurance, they could now invest like investment banks, which meant that they could invest in, you know, whatever kinds of things they wanted, including hedge funds. But look what happened, right? So what happened was, I would say that what happened is that, okay, there are a bunch of institutions out there that are just going to have negative specific heat. Investment banks, hedge funds, you know that they're unstable, all right? But if everybody's unstable, then you're in deep trouble. And of course, it means that there are actually rather simple things that you can do, right, to make things stable again. You can just say, okay, sorry, the bigger you are, the less leverage you get. I'm sorry, that's just the way it is. Because once you're too big to fail, if you have negative specific heat, sooner or later, you're going to meet someone who's just going to suck you up like another galaxy or a black hole, right? So it's just not going to work. Or you could say, it's actually interesting, this says, it's okay to have increasing leverage as long as you're not allowed to invest in all kinds of bizarre like tranches of CDOs and stuff like that. So in a way it says, okay, fine. You guys with negative specific, you guys who can get increasing leverage, you have to make safe investments. You guys who want to make risky investments, fine, you don't get any leverage. And then everything is fine. Anyway, I haven't tried them yet. You're my first audience, and you look like I managed to dupe you so far, right? Something to do with negative specific heat of information.
I can't believe that this analysis hasn't been done.
Haven't found it. I looked all over the place. There's lots of things. You find lots of things about entropy and economics, but you don't find this. There's lots of people who I'm trying out the economists that I know. So far, I haven't found anything like this. Anyway, I just thought I'd share that with you because it's fun, and it is indeed a very direct use of the ideas of information and entropy, which we talked about last time and earlier today. We're just saying, oh, okay, you know, instead of looking at energy, let's look at money. And instead of looking at entropy, let's look at entropy. Right? Because entropy is really something, and information are quantities that can be defined in any system, any situation where you can count stuff. Right? Anytime you can count, number of complexions, number of configurations, then you have entropy and you have information. And these quantities, like entropy and information, can be extremely useful. They can be extremely useful. Now, I don't know if they're useful here. They're useful here at least in diverting you and preventing us from actually learning about coding theory, which we were supposed to learn about, but which you can talk about more next time, and a little bit more today if we feel like it. But they're also useful in a whole variety of other situations. So, and that's what this course is going to be about, and already is about, right? So, all right, are there any questions about this? More questions about this? Anything people would want to say? All right, bear some thinking about. I'll send you copies of the paper when I'm done. So, let's talk about coding theory then. What do people want to talk about coding theory? There's plenty of things to talk about. What is a code?
Any way of transforming entropy into understandable.
I like that. Yeah. So you guys, now you guys, you've got the hang of this. Yeah, yeah. A way, well, any way of yeah. You want to say any way of changing entropy, or let's say information, into something understandable, or
That matters. But, well, yeah.
Yeah, so I think in this case, it's actually not even as complicated as that, right? So a code, I would say, is like a systematic way of representing information, which is actually kind of what you're saying right there. But you can even go further than that, right? It's a systematic way of representing information where some, string of bits, or like set of dots and dashes, gets put into correspondence with another string of bits, or some other piece of information. So what are famous codes? Just mention a few of them. I exemplified it. I didn't mention. I exemplified a few of them. Morse code is a famous code, right? I don't know. Was that? I mean, there have been codes for thousands of years, right? And ciphers, and as well. Though, is Morse code the first one that was used for? Well, I guess you could say that writing is a particularly useful form of encoding, and not even that, actually kind of subtle, right? Because you take spoken information and you encode it as a sequence of symbols on a page. So someone can actually then reproduce the spoken information. That was a pretty darn good idea. You can see why it took people thousands of years to figure that out, tens of thousands of years to figure that out. That's not so obvious. I mean, in retrospect, it's pretty obvious, right? Like lots of stuff, like this, right? Yeah, so writing is a form of code. It's quite an interesting one because you're taking sonic information and you're putting it into, a set of scratches on a clay tablet, or a piece of markings on papyrus, or a set of bits inside a computer. So how do things like letters or alphabets get encoded inside a computer? ASCII, right? So this is that's probably the most common way, right? Do you think? Yeah. Yeah, so ASCII, so coding, so ASCII, which I can never remember what it is. What is it? AS?
American Standard for Information Interchange.
Right, yeah, something like that. I should say that I'm a charter member of the IHA. Anybody know what that is? Yes, I hate acronyms. Acronyms, in my experience, are used primarily by people to make other people feel bad. So you can utter them and you know that the other person doesn't know what they mean. Right, so it's a way of having an in-group and an out-group. And the reason I know this is because I worked for years as a postdoc at Los Alamos, which is a national laboratory. And as a national laboratory, it had millions of acronyms. Everything was an acronym this, acronym that. And nobody, the way that you were real insiders, you knew how to use these acronyms. And you could tell that this was how they were using them, because as soon as I would figure out what an acronym meant and how to use it, then they'd change it. Right? It was actually specifically for this. It was to hide information rather than to make it more accessible.
American Standard Code for Information Energy.
There you go. Good. This is a very cool code. 7 bits. So how many different entries? 128. Yes. I have not tried to teach my children very much over the years, but by God, they do know their powers of 2 up to 2 to the 10th. I figure this will give them a real edge in the coming millennium. Okay, 128 symbols. So this includes all the like typewriter symbols, because this was actually I really encourage you to read about this in the notes. There was because Paul has a very good, very fun, entertaining discussion of this. These are made for teletype machines. Teletype machines recorded information in paper tape. The paper tape had 7 places where you could put holes, and so you could, you could have whole or not whole. And this meant that but they were also made for these, teletype machines. So when you'd feed paper tape into them, then the teletype machine would type out the message. A sound that you never hear anymore. The sound like when you go into a room full of all these like automatic teletype machines, like typing stuff out. Now you go into a computer laboratory and it's like completely silent. It's terrible. Okay, yeah. So that means several things. Like, first of all, what does it mean about 0000000? Sorry, 0000000. I said it right. No holes, right? What do you have to do with that? You automatically have to do something about that, and it better not mean, for instance, A. Why? Why is it bad to have no holes mean like A? Yeah, well, if you have a piece of tape, right? You look at this piece of this tape, there's going to be stuff with data in it. What about the stuff that doesn't have data in it? What does it look like? No holes, right? So if you feed this into a teletype, you want no holes to mean, hey, the message hasn't started yet. Keep on going until you find something that has message. So it's actually null. Like, isn't that's what it's called? NUL. Null. It means there's nothing there. Keep looking. And what about all holes? Do you know what that is? It's okay if you read it or know already. You can tell me.
Delete, backspace.
Right. It means basically ignore, right? So it actually, or delete. I think it is called del, right? All holes. And what it means is that when you make a mistake, you go, shoot, I meant a B there instead of an A. You backspace, you punch in delete, and it puts all holes there. And then when somebody reads it, it says, oh, I'm going to ignore this. It was deleted. Something was deleted there. So that's 127, right? So 0000000 has got to be something special. 127 has to be special. And then there's all sorts of other stuff in between, like, A is equal to 1, 0000001. What do you think B is equal to? Well, you don't even have to guess. Etc. Little a happens to be 1000001. Oh, I'm doing too many. Etc. So there's rhyme or reason here. And the terrible, horrible, awful, awful thing that happened, which happens a lot with codes, because you build them for a specific purpose, just in the same way that nature built the genetic code for a specific purpose. And I really highly, highly recommend, again, as I did on Tuesday, the section on the genetic code there. Often something that seems good for the original purpose ends up being really bad later on. So in teletype, a teletype has like a carriage, right? It's like an electronic typewriter, if you know what a typewriter is. Okay, it's an electronic typewriter, sorry. and it goes, and when it gets to the end of the line, it actually has to go, which is line feed, and bing, which is carriage return. And then goes, line feed, carriage return, bing, right? So when you get the sign for end of a line for text that you're writing on teletype language is carriage return line feed. Actually, you could also do it the other way around, I guess, as well. But anyway, so you use 2 characters to say end of line, go to the beginning of the next line. Now, when you go to a computer, there's absolutely no reason to do this whatsoever. Like why it doesn't have a carriage. There's no return, and it doesn't have a line feed. It's just, oh, this is a new line, started at the beginning. So people, when they started writing things for computers, when they changed from teletypes to like, screens, monitors, they said, oh, why should we use carriage return line feed? Let's just use, carriage return. But then another group of people said, let's just use line feed. So Unix uses carriage return line feed. They use line feed, right. They use line feed. It's Microsoft uses carriage return line feed, and Apple uses carriage return. And what this means is that text that's typed into one computer cannot be reliably translated into text typed on another computer unless you know what kind of computer it was, and unless you have actual information, and it doesn't always work. And if you're like me, who does everything in VI, then actually this happens all the time. Like I try to look at some text that came out of like some Microsoft machine, and it's full of bizarre symbols at the end of each line. It's a big drag. Yeah. So the genetic code is quite interesting in this part. But I don't really have time to describe the genetic code. The genetic code, it has basically DNA has there are 4 different base pairs. There are things that can, units that can be popped in together. So there's A, C, G, and T. Like what, alanine, what are they? Alanine, something, guanine, and, I'm sorry?
Cytosine, guanine.
Say that louder.
Cytosine, guanine, thymine, and then uracil.
Great, there you go. See, I have to confess, maybe I should do this off camera. So I actually never took a course in biology in my entire life. That's like what generation I'm from. Never, not even when I was in kindergarten. Okay, so there are 4 different, you can string these together in 4 different parts. They're complementary to each other. So which is A and T and C and G? Yeah. So these 2 guys are complementary. If I'm not being sexist by calling base pairs guys. I call everybody guys. I call women guys. Okay. So this means that, a typical sequence of DNA will look like this. Something like that. And then DNA is a double helix. So that's one part of the helix, and the other part of the helix looks like this. That's complementary, which is good. Why is complementarity good in this case? While I try to parse what's the next one that I'm supposed to prove. Why is it good that I've got this inverse part over here?
You can have error correction.
You can have error correction, right? Or actually, in this case, yeah, you can have error correction. You actually can do 2 things. You can do error detection and error correction. So first of all, if something's just missing, that's good. Then you can correct it, right? Or you can also find a mismatch. And if there's a mismatch, you don't know which one is wrong. But at least you know that something is wrong. They're next door in the yeah. So let's this is the having. I'm not going to try to cram a whole discussion of DNA into 30 seconds.